This month, we've got a very interesting webinar. We will be taking a look at an EPA-funded Green Enterprise project called PROBOT, which is aimed at developing a new reinforced polymer from PET plastic. Presenting this morning will be Dr. Walter Stanley, a lecturer in mechanics of solids, plastics, composites, aircraft design, and he will be joined by Subramani, Pichandi, and Rachel Kennedy, both UL researchers. And starting you off this morning will be IMR's Romain, Couture, who's our circular economy researcher.
Yes, thank you very much, Gary. Hello, everybody, and welcome to this IMR webinar on the PROBOT project. This webinar is hosted by IMR. IMR is Irish Manufacturing Research. We were established in 2014 by incorporation of ICMR and IComp to position Ireland as a leader in advanced manufacturing. We are an Enterprise Ireland research centre, which works in research that is mid to late stage technology readiness level. Our motto is to demystify, de-risk, and deliver technology in order to help companies to actually unlock the value of these new technologies and develop innovation in their value chains. We have recently announced the Network Circulaire, which is a national platform for circular manufacturing. This platform is sponsored by the Department of Communication, Climate Action and Environment, the Environmental Protection Agency, and by EI Climate Kick, along with 25 manufacturers from large companies to SMEs. Please feel free to check out the website if you want more information. The resource extraction has been growing ever since humankind has mastered energy. Past 30 to 40 years especially, it has been growing quite constantly and quite heavily. You see on the left-hand side is this graph by the World Resources Institute, which shows that every category of material, whether it is biomass, fossil fuel, metal ores, the extraction has been growing so far. On the right-hand side here, you see a graph that looks at the limits to growth report that was published in 1970, and that has assessed how true the modeling was so far. Well, it turns out that the business as usual standard run scenario was actually true. This research pointed out that the amount of resources on Earth should actually start to deplete after a tipping point, let's call it that way. And so far we are approaching the tipping points that have been envisaged by this study. So we need to find a way to reduce the amount of pressure that we put on our system. You see on the left-hand side here, oil is actually one of the materials that is being problematic at the moment. When extracting crude oil, then it is distilled using heat. And you see there is several parts which are actually being made out of it. You have the diesel, the gasoline, the petrol. You extract kerosene as well, ethane and liquid petroleum gas, fuel oil, and you also have naphtha, which is a part that we're interested in. Naphtha is then broken down and polymerized using heat. And this is what becomes plastic at the end of the day. We have extracted so much oil that now we have had to deal with a large amount of naphtha. And naphtha then has been creating a lot of plastic, so much so that the amount of plastic that we have disposed of in an unsustainable manner has been growing a lot more, especially in the past 20 to 30 years. At the moment, there is more than 8 million tons of plastic which end up in our oceans every year. If you want to put it at scale, it means that one garbage truck is being emptied in the ocean every minute. This is what it represents. So it's quite a staggering figure. This is where PROBOT comes from. So PROBOT is a project that has been funded by the Green Enterprise funding stream that has been developed by the National Waste Prevention Program from the EPA. This program joined IMR and IComp together. IComp has developed a high-grade recyclable polymer from PET plastic, and which reduces energy costs and that has a wider processing window than the usual one. Rachel will talk about it later. So IComp was in charge of doing a material characterization exercise, while IMR carried out the market research of it, understood the state of recycling in Ireland today, and understood what are the best opportunities for these composites. So at the moment, the state of plastic of recycling in Europe and Ireland, this is to give you kind of a background of what the situation is looking at so far. Ireland has a recycling rate of its plastic packaging, which is about 31% now. So if you compare it with other European neighbors and with EU average, which is about 40% more or less, it is quite good, but there is still a lot of effort to be made, especially since we look at the targets. In 2019, the target was 22.5%. So Ireland was this target quite heavily. However, in 2025, the Commission has put a target of 50% of plastic recycling, which means that Ireland will need to increase by 29% now, for 19%, sorry. So it is quite an important growth that we need to do here. And as a consequence, we need to improve the way we recycle. Ireland so far generates about 264,000 tons of packaging per year. This plastic packaging, this represents about 60 kilograms of plastic waste generated per inhabitant per year. This is the highest rate in Europe at the moment. Number two is Luxembourg with 40 kilograms. So we are ahead of them by quite a margin. We need to understand the way to actually reduce our consumption of plastic, not only improve the recycling, but also reducing it altogether. So the recycling rate is about 31%, and overall by recovery, which is energy recovery, incineration and recycling, we are at about 95, 96% rates, meaning that there is still a 4% of our materials which still end up landfilled or unaccounted for. So the main recyclers in Ireland, they include Shabra Recycling, which is in Castleblaney, Polyfab, you will have Green Tech Plastic, Wellman, which works with recycled plastic, and so on. The way the plastic is being recycled at the moment, it's important to come back to that actually basis. First of all, plastic is collected. So that's when you put a plastic bottle in your green bin. It is then brought by the lorry to the segregation center, basically at the packaging sorting plants, where all recyclables are separated. So you would have your aluminum cans on one side, your paper on another one, your plastics, PET plastic on another one, polypropylene and all that. Then these are baled and put on the market and sent to a recycling plant. The recycling plant then washes them. There is flaking operations, and after the flaking, then it is being pelletized either by the recycling plant or by a third party. And in the end, you buy these pellets and use them as a secondary raw material to make cloth fiber, for example, new bottles, home textiles, diapers. You have quite a lot of uses. According to Repack, at the moment, there is about 10,000 tons of tea, which is being collected in Ireland today. It is quite an important number, but it means that most of this PET is sent to the United Kingdom or to Turkey for recycling. So that's the state of recycling today. I will now hand over to the IComp team about the material characterization piece of this polymer that they have developed.
Hey, Walter Stanley here. I'm just giving you an overarching view of the, shall we say, the objectives of the study, and that is to make a value-added recycled material. So we're going from a polymeric or a plastic product into an engineering composite. Not an advanced composite, which are used in aerospace applications and Formula One, but for many other sectors such as the wind energy and so on and so forth, and of course electronics. The concept is to take the PET plastic itself and to make two forms. One is a central fiber with its attendant excellent structural properties because of directionality, but to surround that with a lower melting sheath which will act as a matrix. That's what composites are, fiber and a surrounding polymeric matrix. So the manufacturing process basically is to take co-extruded fibers or indeed tapes and to melt the outside sheath, which has got a lower melting point than the fiber. That can be done using conventional hot press means, or indeed we have patented a low energy, quick cycle time, radio frequency heating by doping the matrix. Once the matrix is molten, we then consolidate So in other words, we pack them all together, and in the end is a consolidated composite material with the fibers taking the load and the matrix imparting all of the other concomitant properties. But the key thing is the sheath layer melts preferentially to form the matrix, and the core fiber remains intact. I'll pass you over to our team who have done the processing from pellet form into fiber form and then the characterization. Thank you.
Good morning, Subramani is here. The raw material used in this project is PET, Virgin 1, and PBT and PETG. The PET used as a core, and the blend of PETG and PBT is used as a sheath, which has a low melting point compared to core PET. And before going to the next step, making a fiber, we have to do like rheology testing to check the viscosity profile of this core polymer and sheath polymer with respect to temperature. So which is primary step before the extrusion. So this rheology test we carried out at University of Limerick. The testing mode is isolation temperature mode. The temperature ramp used 2 degrees Celsius per minute. For the core, the temperature range is 250 to 300. And for the sheath one, 230 to 300. So you can see the graph and both the profile, like viscosity with respect to temperature, is very close together. So this confirms that these polymers can be taken into the next step to make a core sheath material. It may be a filament or it may be a tape.
So to go along with the rheology testing, we also have to do DSC, which is differential scanning calorimetry. And what we use this for is to determine the temperature at which your material changes phase. So on this graph, we actually have 3 lines. We have the blue line is the recycled PET, the red is the normal PET, and the green is the bicomponent fiber. The green line is a little bit longer because we actually did a double cycle on this, which I'll explain after. So one of the key points Walter was talking about earlier was the melting of your sheath has to be different to your core. So if you look closely at your green line here, you hopefully can see that before the dual peak at the red and blue line, there is a small peak beforehand in the green. This is the melting of the sheath. The reason that there's 2 peaks is actually really important because this shows 2 good things. One, the fact that there's 2 defined temperatures means that your sheath and your core do melt at different temperatures. So you can isolate the melting temperature of your sheath to make sure that you get the matrix without compromising the fiber. The other good reason is that because it doesn't kind of merge together to make one large peak, means that you have, again, a defined processing window, which is a little bit larger than what's available in industry at the moment with the polypropylene version, which is one of our big strengths for this project. Like I said earlier, this green one is a little bit longer because it was done twice. The reason we did it twice is because this was a cradle to grave to cradle material that we wanted to be able to reuse it after it had been, its life cycle had been ended. So this second peak here on the other side is the melting temperature of your overall combined material. So this is the mixture of your sheath and your core. So this is a slightly different temperature. It's nothing drastic. It's only 2 degrees, but we still need to know exactly this temperature because in industry, obviously, if you're going to do some melting of this, if it's going to be at 2 degrees higher, making sure that a large machine is 2 degrees higher than it is for the production, it's a significant difference.
As a part of the project, we did a comparison of PET with respect with recycled PET and in a pellet form. So this both pellets are pressed into a panel by using a cover art press at University of Limerick. Then we extracted samples for the tensile test, flexural test, and compressive test. And the results given in the table, and it shows that except flexural modulus and compressive modulus, remaining all the values are decreasing compared to PET. Means the recycled PET shows less value. And in case of TG, this is very important for any processing of polymers, especially thermoplastic. So both PET and RPT is very close with around 2 degrees Celsius difference the TG is like a softening temperature. It's a border temperature where the solid state become a rubbery state. And next stage is to develop a bicomponent monofilament, which is carried out at Centexpel VKC Belgium. It's a research center where they have the facility to develop this bicomponent fiber, as explained in the first material characterization. Before step into this process, we have to combine the PETG and PBT, which is carried out by using twin screw extruder. So we blended there in extruder and produce the filament, and then filament converted into pellets. These pellets taken to the Belgium to make a bicomponent. So the core will be the 100% PET, and the sheath will be the blended pellets of PETG and PBT. So the property is given in the table. The fiber diameter is in micron, 290 to 300, and the fiber titrate is a Decitex, and this is a fineness. It's the linear density of the material, which is 870 to 890. And the fiber strength is centinewton per tex, 43 to 50 centinewton per tex. So the centinewton, the tex are equal to gram per tex, and this is like maximum load withstood by fiber divided by the tex of the fiber. And the draw ratio used to in this fiber manufacturing is 6, and the core sheath ratio is 70-30. The core will be 70 and the sheath will be 30%. So this is the facility used to develop bicomponent at Centexpel, Belgium. The next step is like after fiber filament manufacturing, we have to convert into the fabric. The process is the whole process carried out at Axis Composites, Belfast, which is in Northern Ireland. First, we have to convert the big bobbins to small bobbin. This is the left side, which is shown. And this bobbin is used to convert a warp beam. And this warp beam, also the same small bobbin used to develop, produce a shuttle, like a shuttle bobbin. So the Axis Composite has the pilot weaving machine. It's automatic shuttle loom. So we developed the fabric, which has 1.3 mm thickness. So now the next stage is to develop a composites from using this fabric, which is carried out at University of Limerick using Carver art press. We use 6 layers of this fabric. The temperature is 235 degrees Celsius. The consolidation time 5 minutes with the water cooling, and the load is 42 kilonewton. It's pressure 1.5 kilopascal. The consolidated panel thickness is 2.5 to 3.3.
I'm just going to do a quick overview of our characterization results. So we have a couple of tests that are standard to be done that you would expect to find results of in any technical data sheet. So you have the tensile results here, and the most important part here is that they're all very consistent, very uniform, nothing unusual happening. The compressive here on the right does have a slight toe at the start. This is just due to any kind of settling in the fixture. The majority of the compressive strength results are in the center linear part of the graph. The other tests we did were flexural and SBS. Flexural is another one that is standard in the technical data sheet. This is just the bending strength it has. SBS is a little bit more unusual, but we did feel it was necessary to do just because this is short beam shear, and this is to make sure that we had good consolidation between the layers. Because we were layering it up and compressing it down, we wanted to make sure that there were no delaminations or pre-existing cracks or voids or anything, and the SBS is one of the best ways to see that. These 3 graphs are the results that you get when you do dynamic mechanical analysis, or DMA. This gives you the storage modulus, the loss modulus, and the tan delta. Each of these gives you a TG, which, as I said earlier, is the softening point of your material. In the storage modulus, it's normally the lowest value of TG, which is related to the mechanical failure. The loss modulus TG is related to the physical property changes and its strength. And then your tan delta is a higher TG value, and it's the midpoint between glassy and rubbery, where it's a bit leather-like. Our TGs that we used, we took from the loss modulus because it was the median value and it was related to the physical property changes, which is what we were focusing on. This is just a summary of our all the results we have. So you have the various strengths and moduli. All of the values have a plus or minus of a standard deviation, which is just the range of values that our results fell within. And then in brackets, you just have the standard error for testing. This is probably the most relevant that we can give you. This is the flexural comparative table. In the first column here, you'll see the curve PP materials. So this is what's commercially available at the moment. It's a slightly different makeup. This is a polypropylene as opposed to our PET material. What we've compared this to is the unreinforced virgin PET, so just a standard plastic compressed from the pellets. So this has no reinforcing fibers in it, which is the added advantage of composites. It still has an improvement in flexural strength. We have a slight decrease in modulus. The Serpet is in here twice because we had a pilot version of this project to see whether it would be viable. So that's the first results we have. It does have a drastically better flexural modulus, but a lower flexural strength. But this was done with material from different suppliers. We had a different manufacturer. So we're going to focus on the Serpet PROBOT one, which is the one that we made during this project. And this is better in both of the properties. We have an increase of 16% in strength and 8.6% in modulus. This improvement is also better than your unreinforced, which is why we like to do with composites. So your unreinforced would be the equivalent of just having your matrix, whereas your Serpet PROBOT has your matrix with your reinforcing fibers in it, which is why it's so important to make sure that your sheath is at a melting temperature that is different to your core to ensure that your cores remain intact to provide this additional strength that we want.
Thank you, Rachel. So now I'll walk you through the business case and through the business data that we've gathered. So first of all, you can see here the price of recycled PET since January till July, and in August it kept decreasing a small bit. The price of recycled PET is actually fairly volatile on the market. Demand is being mainly driven by manufacturers who have the likes of interest in environmental KPIs to incorporate recycled products into their businesses. And theoretically, that would be the point of this composite, to actually be able to incorporate recycled PET into this mix, sorry. So to create 1 square meter of composite, then you need about 25 kilograms of raw PET, but this is at lab scale. So we expect this number to decrease substantially when you go to industrial scale, because you have reduced waste, for example. Replacing virgin PET with recycled PET, if we just have a replacement rate of 25%, that would reduce the embedded emissions by about 18-20%. So it is already quite important, and it's important to I think, highlight this data. So as Rachel mentioned, this self-reinforced polymer, so it's a direct competitor of the curve composite, which is made with polypropylene at the moment, as opposed to polyethylene terephthalate in this one. As a consequence, we can extrapolate that Serpet can actually be used for applications in the automotive industry, sandwich structures, sports equipment, farm machinery, protective equipment, or audio and technological equipment. There is machinery that is required for this, for processing this Serpet. So you see the shredder, an extruder, a filament extruder, weaving preparatory. So integrating this this production into your own facilities might prove complicated, or might require an investment anyway in the first place. But in the end, working with companies that already are in this work is kind of envisaged, should be envisaged. So Serpet in a circular economy, can it be embedded actually? So first of all, we talk about sourcing of secondary raw material. There is an opportunity to find new PET feedstock, new waste PET, and that means that actually that would augment the supply of produce and therefore decrease the price. There is a study at the moment being done in Germany to recycle PET food trays, for example, or PET blisters, which is quite promising, and that could be interesting to bring into Ireland. Design for sustainability. We would like to incorporate recycled PET from the design stage. At manufacturing scale, the fact that there is a wider thermal processing window means that actually there would be reduced waste in the manufacturing processes. In the use phase, this product is robust and has a very long life cycle, which is critical when we talk about plastic. Plastic at the moment, there is quite a lot of plastics which is still being used for single use, and this is what causes the problem and what pressure on our societies, but create robust, with a long life cycle products is doable and would be actually a good answer to this crisis. And finally, at the end of life, surplus is fully recyclable and is recyclable by design. So that product in the end, that composite would be not fully circular, but would already bring quite a good amount, could tick a good few boxes of circularity. So the strengths of this product, so it can be made with various amount of recycled PET theoretically, and is easier to process than its curved competitor. It has a rapid processing and it is recyclable by design. It is still unclear how much recycled PET can be incorporated, and that's one of the recommendations for further research. A large initial investment is necessary, so that's why we recommend to actually work with companies who already have this sort of machinery, or to use it just for research anyway, just for innovation purposes. A big opportunity of that material is that companies are now, they have KPIs to seek environmentally friendly alternatives. So if you supply a company that has these KPIs, then your product would actually be better than the competition's. Member states have agreed to a higher collection targets for recycling plastic bottles, and therefore there is a need to actually improve that rate, and creating higher value adds answer to actually get a better collection system and get a higher collection rates. Consumers' awareness towards plastic litter is improving, and there is a higher willingness to pay from their side for eco-friendly products. And finally, there is PET products which are not yet recycled, but fully recyclable yet. And finally, about threats. So the main one here, the main takeaway is that plastic is actually a byproduct of oil. So as long as oil production will keep, oil will keep being extracted, then plastic will be produced. So as a consequence, it's important to actually do plastic right, and to do it with a long life cycle and recyclable by design, which is one of our recommendations. And in the conclusion, so first of all, this polymer has a very high potential to increase the recycling rates in Ireland and to give recycled PET a much higher value add actually. Plastic is a very strong, it's a cheap material, it is convenient, it is an exceptional material to use. It is just us that have to learn how to use it better. And we need to find ways to make long-lasting plastics that is reusable by design or recyclable by design, and instead of these single-use packaging containers which we have. Finally, for future research, the team would recommend that more research be undertaken on the amount of rPETs to be incorporated into the composite at various stages, and to still make a composite which is commercially viable and which is still better than the curved one. And finally, a scale-up should be carried out to determine the costs incurred in the production of this product at industrial scale. So thank you very much, everyone. We are very happy that we have been able to share these results of this study with you. And I would like to personally thank Gary and Walter and Subramani and Rachel for this research, and David McCormack as well, and all of the industry and EPA partners who have helped us carry out this work.
Thank you, Romain. And yes, thank you, Walter, Subramani, and Rachel. Thank you all for joining, and keep an eye out for our upcoming events and webinars. And if you have any other questions that you want to email myself or any of the team on this, let us know. Thank you and goodbye.
Thank you all. I'd like to thank IMR for significant efforts put into the market and the sector viability of this application.